Thank you. Yes, I feel honored. So I can eat bistecca at dinner? I'm allowed? All right, guys. So I just received a compliment, so I can do whatever I want, right? Yeah. So where were we? We were using fancy words, cohomology, and so on, equivariant. Yeah. Some of you asked me about some more refined questions about the mathematics of this. And I kind of refused to answer them a little bit. So I asked Davide to put a link to lecture notes by Cremonesi, where things are explained in some more detail. They're not mathematical lecture notes. He's a physicist, but they summarize the math a little bit, more rigorously. And of course, there's whole books on equivariant localization. It's a field in mathematics. So yeah, if you're interested, go and read more. Okay, so where did we stop before lunch? In the infinite past, we wrote this formula.
Sorry, in the shot there is still the control panel in the shot in my screen I can see the control panel of the camera, and this covers some of the screen.
Apologize, now fixed.
Okay. Thank you. Sorry, I didn't mean to interrupt.
Yes, so hopefully now everyone can see. This is where we ended. So you have some kind of equivalence between observables related by Q-exact operators. Okay, I have to say the correct words, that what I mean by this averaging is actually that I'm sitting at a supersymmetric vacuum, otherwise I don't have Q at all, it's broken, so I'm assuming all of that. So now I can push this to the extreme and conclude, so I can exponentiate this, so any power of Q is going to be fine, and so the claim is that the expectation value of this operator, or products of operators in general, is actually can be written like that. Okay. So if I put t to 0, I have basically the definition of the expectation value. But since nothing is affected by Q-exact terms, I can add an arbitrary Q-exact term. Okay? So I should be a little bit careful here. So this PF is some kind of fermionic functional of the fields, very abstractly. That's why it has an F here. And I should be careful that I'm not adding random stuff. This should still be obeying the bosonic symmetries. So I have some mild conditions that PF of phi is invariant under B, where B is the bosonic symmetries. And then the second thing that you may worry about is that you're adding something, okay, it's Q-exact, but it's wildly fluctuating or some exotic functional that's going to spoil this asymptotics that I'm assuming so that the path integral converges. So QPF phi has nice asymptotic behavior or fall off. So what this word nice means, essentially no one knows, but Right, so this is the abstract claim. So now, it looks like I have introduced a parameter t in the game, and the claim that I'm going to make now is that nothing is a function of t. Well, nothing supersymmetric is a function of t. Okay. Yeah, because this is very general, so I can expand this exponential. Yeah, so that, yeah. I'm not sure what the confusion is. You are confused this by this multiplying that, or? Well, I can move the Q acting on this, right? All BPS is Q closed. I'm using that, yes, I'm sorry. I should remind you that Q on all BPS is 0. So I can, if I have a Q that is not hitting here, I can just pull it back and then. Yes, so the claim now is that nothing, well, here's the claim in equations, that if I take a derivative of this quantity, well, you can, t appears only here, you get the following answer. So I think I'm answering exactly your question right now with this calculation. Okay, so, sorry, this is Q. So I put down a power of Q, PF, because of the derivative, and I get a minus because there's a minus here. So now I can do what I told you. I can put this parenthesis all the way up here because everything here is invariant under Q. Q on all BPS is 0. By assumption, the action is invariant under Q. And here I already have a Q. Q square vanishes. So, well, Q square is equal to B in general. Q square doesn't vanish. That's the equivariant part. So if Q square vanishes, you have ordinary cohomology. If Q square is some other operator, you have equivariant cohomology. So, but P is invariant under B, and so Q square is B, but PF is invariant under B, so I get 0. And so all of this is to say that I get this. Okay, and now I'm again assuming that the measure is invariant under Q, and I get 0. Okay. All right, so now I have a powerful statement. This expectation value of the BPS operator, or product of operators in general, is independent of t. So I might as well evaluate it at any value of t I choose. This is similar if you've done anything with differential forms. You know, there's closed and exact forms and so on, and there's always a harmonic representative that is annihilated by d and d star. And that's usually the nice guy to choose in the cohomology class. So such choices you're free to make when you have cohomology. And so I claim that a nice choice is to take t to be very large. In fact, infinitely large. Okay? But now, when t is very large, I can use the stationary point approximation and find the answer. So the integral is dominated by the zeros. So to be more precise, this observable is dominated, or in fact computed only at the zeros, dominated by saddle points, as they're called. Saddle points or solutions of the localization action. So this is another thing I'm introducing as a name, QPF of phi. So I'm thinking of this PF as it is a fermionic functional of the fields. Acting on it with a Q makes it a bosonic thing. It's some functional of phi, which I call the localization action. And I have to find the critical points, the solutions of the equations of motion of this action, and then use this saddle point approximation or stationary phase approximation. Okay? So that's my job. Okay? Is this argument clear? Yes? Okay. It's an abstract argument. I'm emphasizing it is really, every equation here is very schematic. So you should keep that in mind. And since it's a path integral, we are really, the level of rigor is not maybe up to the standard of mathematicians, but sometimes it can be made up to mathematical standards. Okay. So the stationary phase approximation was this deal where you find the classical solutions here of this action now. So I do this. I find the classical solution and add a small fluctuation around it because I may have non-trivial fluctuations. So to indicate that this is a small thing, I put 1 over square root of t. This will remove, when I was doing the stationary phase approximation, I have this prefactor 2 pi I over t to a power L, and L was the dimension of the manifold. Okay? Now here I have my manifold is field space that's infinite dimensional, so I should be careful with such prefactors, and that's why this is a convenient normalization. Okay, so S becomes S of phi 0 okay, plus a quadratic fluctuation phi evaluated at phi equals phi 0 d phi squared. So this is what we did on the classical piece and then on the harmonic oscillators. Okay, so now you've done something amazing. You've converted a mysterious object, a path integral, of a general supersymmetric quantum field theory into something that is a classical contribution and a Gaussian integral. So now I have to do only the integral, the path integral over these fluctuations of the fields, and these are, well, quadratic, so I have e to the minus x square kind of integral, and that's exactly solvable. Okay? So the bottom line of this operation is that you have to integrate, yes. So if you wish, I'm splitting the integral now, the path integral, into integral over these fields, and then a path integral over the fluctuations. And the path integral over the fluctuations is going to give me the standard determinants that you study in quantum field theory. When you study the path integral of a scalar, you get a determinant in the denominator. When you study a Gaussian integral of a fermion, you get it in the numerator. So for every fluctuation of every field, phi, you would have to compute a determinant like that and you know, add it to the story or multiply by it. Okay. And this, again, this is super schematic. So this integral goes only over the space of solutions of this equation here. So that's how I denote it. And these field configurations, the saddle points, are automatically supersymmetric, meaning that they're annihilated by some supercharge. So you have to integrate over what's called the supersymmetric locus, okay? And then this is just evaluation of the integrand at those points, and this is the Gaussian integral already performed for you. This is just some schematic way to write what I told you about determinants of bosons and fermions. That's it. So the claim is that this is the full answer. Yes, yes. Well, right, so if you, yeah, this is super abstract at the moment because I haven't told you anything. Yes, you have to, so there's a few pieces of art here and a few subtleties in addition to what I've already told you. One piece of art is to find this guy, PF. Right? It's not, this is not algorithmic in a sense. You have to find some PF, you have to, that is invariant under this B, and then you have to solve these equations and find the solutions. So I will give a detailed example now so that you can see how it works at least on an example. But a general algorithm, so in general, this will be hard. This, by the way, this locus here, someone asked me in the break, I still haven't won the game, right? So it could be that this is still some complicated field configuration that, so this could still be a path integral, right? In general. And so then I've reduced the path integral, so I kind of partially did the path integral, but still got a path integral over some smaller set of fields, but still a confusing object. So you really win if this configuration is nice. So if you get something that localizes to points and then you just get an ordinary matrix integral, for instance. No. In general, this is still a path integral. Yeah. So no winning has been achieved yet. Good. So some maybe boring comments, and maybe it's obvious to you, but it could still be confusing for some people, so I want to emphasize. So here I'm doing a stationary point approximation in a parameter t. This t is a totally auxiliary parameter. It has nothing to do with h bar. Even though I'm doing this operation that sounds like WKB approximation in quantum mechanics, in everything I was doing, h bar is equal to 1. The coupling is whatever it has to be. I have not done any classical approximation to the quantum field theory. It's only this weird Q exact term that I've added, and I just use this t as a parameter. So this is a fully quantum result. Okay? meaning exact. Whether it's computable depends very much on the case. It depends on whether I can actually do this integral and whether I can compute this determinants. Okay, done with the general story. What do I have? About an hour? No, a bit more than 1 hour, right? Okay. Okay, so now I will go into some very specific example. I gave you some reference on the website. It's by Silvio Pufu. So it's a review on applications of supersymmetric localization to 3D n equals to 2 QFTs, which is precisely what I've been talking about during this week. So there's more detail there. And this review of Silvio is only one chapter in a gigantic, literally 1,000-page review of supersymmetric localization in quantum field theory and various applications. It was written in 2016, I think. So if you're really into this abstract nonsense, you should go and read about that. It's literally 1,000 pages. All right. So we're back to 3D n equals to 2 super SUSY quantum field theory. So I will not even be conformal at the moment, so I'll keep things general. But we'll study these things on S3. So this is a non-standard thing to study. You know, in QFT, you may be used to the fact that we go from a Lorentzian to Euclidean, but usually we looked at QFTs on R3, or maybe R2 times a circle, but S3 is probably not very standard. Okay. The reason we can put supersymmetric quantum field theories on S3 is that S3 is nice. It admits many killing vectors, but it admits also killing spinors. So this A is the radius of the sphere. So I keep the radius explicit just so that you can see what happens when A goes to infinity, and that's the limit where I get R3 back. So this is a covariant derivative acting on spinors. Do you know how it acts? No one's convinced. Do you know what the spin connection is? So this acts like that. So you have to compute a connection, which is very much like the Christoffel symbol, and then gamma matrices, and then you act on the spinor. That's what this covariant thing is. Okay, so then I have, this is the round sphere. Okay, you can, let me be, I hope I get it right because I don't have it in my notes now. Someone from the organizers will correct me if I get it wrong, but I think that's correct. So this is probably not the, well, this is something I'll use later on. So this is the metric on S3, written in a somewhat maybe strange way that you might not have seen. S3 can be thought of as a S1 fibered over S2. It's a non-trivial fiber bundle. This is called the Hopf fiber, or the Hopf fibration. And you see that here because there's a non-trivial connection. This has deep connections to physics. For instance, this one form is precisely, it's not a one form as written because I forgot the D, but now it is. So this one form is precisely the gauge potential for a magnetic monopole at the center of S2. Magnetic monopole of charge 1. the degree of the bundle is 1, and so on. So there's beautiful mathematics, but if you don't like that, ignore. It's an explicit metric on S3 of radius A. Okay. Sorry, yeah, see, these are two-component spinors, so the gamma matrices are the Pauli matrices. So I was writing here general, so this is a general covariant action on a spinor. In my case, these gammas will be sigmas. I need something to convert. You get 0 if you put A to infinity. So, you're used to the notion of killing vectors, right, on a space. There's also the notion of conformal killing vectors. So you have also killing spinors that solve this equation that you seem to like. You're emotionally attached to this equation, right? Okay, so if you are, then you go home and you compute this. Okay? And then you will soon find, after correcting this an impressionistic equation, you'll soon prove that the curvature, the Ricci tensor, has to vanish. Okay? So also in high school, you learned that the sphere has a non-vanishing Ricci tensor in general, especially with this metric, and so you'll have a problem. And you solve the problem through adding this term. Yes. I mean, this is a very pedestrian explanation, but there's like this beautiful stuff that you can say about this. Special holonomy manifolds and G structures and things that I don't understand well. But yes, they are true, even if I don't understand them. Anyway, but this you can convince yourself that this equation leads to the curvature vanishing. Yes? Because it kills everything. I think I've had this confusion, and maybe I don't like reading math books, and people call this parallel spinners and so on. Yes, call them whatever you want, but they obey this equation. What's the correct language? Do mathematicians use killing spinners, Davide? Right. Right. So that's a good point. It really depends on how many of those you have, but suppose that I have two complex conjugates. I'm very schematic. And you take this. So this has two spinor indices, you contract. This looks like a vector, and it is. And then you can ask, does this obey a nice differential equation? And as Davide points out, it's killing. Yeah. But sometimes you can just have one spinor, and you don't have a conjugate, and then, right? Then you may not have an isometry. You may not have a killing vector. Why are we talking about this? Oh yeah, so the existence of this guy so in general curved manifolds, you don't have, even if they're spin, right? You don't have nice spinners that allow you to generate some kind of translation in superspace. So we are after actions invariant under supersymmetry. So it's very easy to put a bosonic theory, even a fermionic theory, on a curved space. You just, every contraction that you make with the metric on that space. That's what you learn in a GR course. But we also have this extra condition that we want supersymmetric action, so we need some parameters epsilon that are somehow covariant on this curved space. On flat space, we just used the constant spinner, and that was good. On these manifolds, the special holonomy manifolds, in some sense, these are covariantly constant spinners, we can use them. But S3 is not like that, or generally compact curved manifolds will not have that. And so you really have to worry about, can I put a supersymmetric quantum field theory on a curved manifold? And there's a systematic way to study that question, which we will not do. But this is supposed to convince you that on S3 it sounds plausible. Okay, so now at this point, here it says that the Simons Foundation, so your lunch is being paid by Jim Simons. I hear it's not a very generous lunch, but you know he's not that rich. So this goes recorded again, and anyway, I'll get lawsuits and whatnot. So Jim Simons is whatever, the 23rd richest man in the world or something. So he's very rich. But before he wanted to become rich, he wanted to do math for fun, and so he did. And you should, if you don't know much about him, you should read about him. But he was one of the people who found a very nice action, or a very nice differential form. It's called the Chern-Simons action. And it finds many applications in physics. So the theories we're going to study are actually going to be gauge theories for a little bit. And they'll have the following actions, schematically. So there'll be three-dimensional gauge theories, and they will be constructed out of two types of multiplets, which some of them already we talked about. So the first one is the vector multiplet, which is appropriate for a gauge field. So here is, again, what you asked me about. So now this multiplet has a gauge field, A mu. There's some gauge group, which I'm not specifying at the moment. Lambda, which is a spin 1/2 field. Sigma, which is this real field that you asked me about. And D, which is again real auxiliary field. Okay, now I also have our friend, the chiral multiplet, which has a complex, a scalar, two fermions, and an auxiliary field, F. So now these are my ingredients that I should start writing actions with. Something that maybe you've heard is that in the Maxwell term, the Yang-Mills action, F mu nu, so from A mu I can of course construct F mu nu. This is a connection on a gauge bundle, this is the curvature, blah, blah, blah. And you can construct this action. Well, you can then ask, this is an operator, is it relevant, irrelevant, marginal? You can do the counting, and in 3 dimensions, this is an irrelevant operator. Okay, so at low energies, this will flow to 0. The coupling, the Yang-Mills coupling, is not going to affect the low energy physics. Well, Professors Chern and Simons inform us that there's another option to write down a kinetic term for a gauge field. And of course, in hindsight, all beautiful ideas are obvious, and it applies to this one too. It's almost anti-climatic what this action is. It's the obvious one. I'm just writing down explicitly what this action is. So I have to take a trace over the gauge group. And I missed something. Yeah, I missed an epsilon in my notes. The i's are sprinkled around because I am in Euclidean signature, and so these i's come from, weak rotating, let's say, if I'm in Minkowski space, I have to put some I here in one of the coordinates, and that's this I. Okay, so this action, so the trace is over I mean, each of these A's is in the adjoint of a group G, so I have to sum over those indices. And that's the trace. A is the gauge field. In general, I'm non-abelian, so the commutator doesn't vanish. And this is the Chern-Simons term, the Chern-Simons action. So I've fulfilled my contractual obligation to mention the Chern-Simons action. We can move on. So one thing that you should, if you don't know about this, you should read about it, first of all. But this is, to define this action, I don't need a metric. So it's a purely topological action. It can be written in terms of differential forms as A dA minus 2/3 A wedge A integral over a manifold. So nowhere do I need to talk about a metric. So this is maybe the simplest example of what's called topological quantum field theory. Okay? This, so the equations of motion here, if you wish, do not lead to a propagating photon. So if we lived in such a world, we would not be able to see each other. But we don't. And even if we lived in 3 dimensions, if you add matter fields that couple to the gauge field, the theory is no longer topological. And that's what we're going to do here. So this is way too explicit. We're not going to use all these details, but anyway. So I should also say that every time I'm using tilde is because I'm copying from the notes of Silviu, and he's careful, as he should be. So we're in Euclidean signature. So every field is complex, and things that are related by a complex conjugation in Lorentzian don't have to be so in Euclidean. So that's why tilde means a bar. Okay. So that's this Chern-Simons term. So this is the usual Chern-Simons term for only a gauge field, but here I have a whole multiplet of supersymmetry. So I have to make it supersymmetric. And the claim is that this is the supersymmetric Chern-Simons action. Okay. Good. The coupling K. K has to be quantized. This is called the Chern-Simons level. It has to be quantized for topological reasons. I don't have time to explain this, but there's a quantity here, K over 4 pi. And then when you integrate this over a manifold, you can prove that this K is quantized, but depending on the conventions, integer or half integer. So K is like 1 over G Young-Mills, right? That's the gauge coupling, but it's protected in a sense. It cannot be affected by an RG flow because it's discrete. All right. S kinetic. So this is a more pedestrian thing. I also have a trace. Yes. Well, I'm not going to write these indices. So in general, I can have many such fields. I will write this action for just one, because otherwise I would just have way too many indices. So these covariant derivatives, I don't have to write them like this because I have a scalar, but I just want to emphasize that everything I'm doing is on a curved manifold. So you should not forget that. So there's an interesting coupling here, okay? This sigma is this real scalar field that I was asked about. here. And this R is the U1, the charge under the U1R symmetry of the field phi. Okay? And this coupling, as you see, so the first one exists in flat space. It looks like a mass term, and indeed, sigma is called a real mass in colloquial SUSY talk. But this guy is only there on the sphere. This is really needed to complete the SUSY transformations on the sphere. And of course, if R is equal to 1/2, it vanishes. So that's something to pay attention to. And there's other terms. Chi plus I, chi transposed I sigma 2. So this is now, so this is the kinetic term for, so this sigma mu, so this is really the Dirac operator on S3, sigma minus I, R minus 1/2 over A, chi. Then I should keep on going. Not sure what's the most, it's a long action, but I want to emphasize a few parts of it. That's why I want to write it down. So this looks like a mass term for the fermion. And again, there's an extra contribution from what you're used to that must be there because of supersymmetry. I have minus F tilde F. Then I have Ukavas, lambda I sigma 2, tilde, no, transposed, whatever. Phi tilde chi plus chi tilde transposed I sigma 2 phi lambda tilde, the conjugate of that. Then minus D minus R minus 1/2 over A square phi tilde plus 3 over 4A square phi tilde phi. This closes that bracket. So I'm, sorry. This is not boring, okay? Sorry, I should emphasize. The covariant derivative on a scalar, so I'm combining gauge covariant. So this scalar field can be charged under the gauge field. I'm normalizing it to 1 charge. And then also the fermion. The fermion is charged under both the curvature and the gauge field, like that. And this R is U1R charge. Okay. There is also the interaction term, the superpotential term. I'm going to write it down, and then I'm going to make some comments. So it's really, that one is the boring one that we have seen. And then the complex conjugates, Phi tilde. So the notation here is that every time I have an index, so I'm assuming now that I have multiple chiral superfields, every time I have an index, so omega I is 1 derivative with respect to phi I of the superpotential, and omega ij is 2 derivatives. Phi I d phi j of omega. So this part of the story is precisely what we had before when we have only chiral superfields, right? This has no knowledge of the gauge field that I've introduced, and the only thing that changed is that I'm doing an integral now over S3 instead of R3. Okay, so that doesn't need too much explanation. This kinetic term needs explanation. So I have some kinetic term for the gauge fields here, this Chern-Simons piece, and I have kinetic terms for the scalars. So now you can take a point of view, like if I have kept the gauge coupling, or if I had kept here the charge, if you wish, I could have carefully taken a limit. Anyway, I can make the gauge field non-dynamical, meaning I can remove this term and still ask, so I have a chiral superfield on S3, but I can also turn on a background, if you wish, a magnetic field, so to say A mu. But if I want to do it in a supersymmetric way, I have to turn not only A mu, but the whole multiplet of A mu. So A mu, lambda, sigma, and D. All these fields come in, so I have to turn a supersymmetric background magnetic field. Okay? If I want a supersymmetric action. So this action that I call S-kin gives me the rule for that. So this action can be interpreted as a coupling of a electron, a chiral superfield, to a gauge field, a dynamical thing, or it can be interpreted as the action of a chiral superfield in the background of a curved metric, S3, and a supersymmetric magnetic field. And then, going into the details of the action, you'll see the coupling. So here, in this term, is hidden the coupling of the scalar to the background gauge field. Here, in this term, is hidden the, well, it's not very hidden, it's very manifest. There's the coupling of the scalar to the scalar coupling in the background field. So this is now a non-dynamical object, but it has to be turned on for supersymmetry. If you turn on the gauge field, you have to turn on this. This comes from the fact that the manifold is curved. Here, I have another. In this nabla mu, I have a coupling both to the curvature of space-time. Here, there should be a spin connection somewhere. Sorry, this is probably omega. Sorry. So this encodes the curvature of the metric. I see what happened. This is already computed because the spin connection of the sphere is very simple. Anyway, what I just erased was the answer on the round sphere. Anyway, in general, this is what you have to compute, and this is the coupling to the background field. And we can keep on going. So this is now how the fermions couple to the background sigma and to the background to the S3. These are just Yukawa coupling. So these actually you have in flat space also. And this one is more of that. In this spirit, it's the conjugate of this roughly. And this last one is a pure coupling to curvature. So even if you have a simple scalar field on S3, so if you start from the Lagrangian d mu phi squared on R3, begin with this, and think of this as a conformal field theory. It is a conformal field theory, a boring one, it's a free theory. And then you observe, or you read in a book, that R3 and S3 are related by a conformal mapping. There's an explicit conformal mapping between R3 and S3. And you can then ask, well, I have a CFT. I can, if it's invariant under the conformal group, I can work in any conformal frame I want. And so I can go from R3 to S3. That's right, but when you do conformal mappings, you have to do it in a covariant way. So going from the metric on R3 to the metric on S3, you'll pick up a prefactor in the metric. And so you have to transform this field according to its conformal dimension, and when you do that carefully, you get this prefactor. So this is what's called a conformally coupled scalar. And this coupling is purely induced by the fact that you want, when I turn off every interaction and I have a free theory, I want to have a free conformal theory on S3. That's what this ensures. Okay, the superpotential I've already said is just like in flat space. Any questions about any of this? Yes? They can be dynamical. Just the first term. Well, correct. Well, yes and no. So I have a full multiplet, this vector multiplet, and if I can write down two supersymmetric actions for it, this and the Maxwell term. But the Maxwell term has to be completed with the kinetic terms for the lambdas. And so that whole term has been integrated out, has been frozen, if you wish. That's why you don't see the dynamics of these guys, roughly speaking. But if you were to include also that term, to have a Chern-Simons term and a Maxwell term and these terms, it will still be supersymmetric. However, for the dynamics of the theory, those at low energies, they'll be frozen. So I'm not sure that answers your question. So these things have kinetic terms that live together with the Maxwell term, if you wish. Lambda and sigma. D does not have a kinetic term, it's an auxiliary field. Yeah. 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 Well, in some sense, yes, what you're saying is true, but I wouldn't call this a supersymmetric theory because you still have to, even if they're, I'd say, auxiliary, you still have to include them in the SUSY transformations. So that really, you need this piece in the action to make it supersymmetric as an action. But then this theory has indeed no dynamics by itself. Yeah, because there's no kinetic terms, no propagator. Well, this looks like it may have a propagator, but the equations of motion are going to fix you to that you don't have a propagator on shell. Mm-hmm. Yeah, which is what I said at the beginning, right? I'm not sure what. Right. If you only want to keep the Chern-Simons action, including these two pieces, and if you're on a manifold like S3 without a boundary, that's it. You don't have any dynamics. Dynamics can be induced if you have a manifold with a boundary, so you should be a little bit careful. Condensed matter people call this edge modes, right? On the boundary, you have a two-dimensional boundary, and each of these modes can actually have something happening on that boundary. And this will lead to propagating boundary and degrees of freedom in general. Yeah, I'm not sure what else to say. And if you have started with this action and you put a boundary and you put the correct boundary conditions, then you'll have dynamics on the boundary and it will be supersymmetric because you have included these two terms. But yes, on S3, nothing interesting happens. Yes? Yeah, that's one way to say it, yes. You get massless modes because it's topological, yeah. yeah. I mean, there's deep relations between Chern-Simons theory and the fractional quantum Hall effect. The quantization of the conductivity is related to exactly this quantization, all that good stuff. David Tong has very nice lecture notes accessible even to me, so you should read them on his website. In general, you should read his whole website because he has amazing lecture notes, but specifically for that, yeah. He should be invited to he should be the only lecturer at every school. So to all organizers, I mean, why do you invite me to speak? It's like... yeah, I have one more term, right? The topological term. Okay, this is going very slow, but anyway, I'll make a mention of that term. Before I make a mention of that topological term, I want to emphasize that this is going to be supersymmetric only upon a certain condition, algebraic condition. And that is essentially that the R charges of all fields have to sum up to 2. I'm not going to write it down because, you see, I have these parameters R, and for every chiral superfield, it has to, it will appear there. But you should ensure that the superpotential W, which is some kind of sum of monomials of chiral superfields, that each of the terms in the sum has R charge 2. Because otherwise we'll not have supersymmetry. So that's a constraint on the numbers R in this game. All right, so that's one comment. Another comment has to do with this topological term. I'm going to write it down. Again, there's an A here. So when you go to the flat space limit, it goes away. I d plus sigma. So I'm putting hats here. And actually, I don't need a trace, by the way. So this term appears if you have a U1 factor in the gauge group. Okay. So if your gauge group is U1 or something like UN, which is the same as SUN times U1. So for this piece of the UN gauge group, or for if you just have a U1, you could write a term like that. Why is that? Well, you're in 3 dimensions. So every time you have a dynamical gauge field, you can construct a current out of it, which goes by the name of topological current. Trace is not needed. Okay. I can put a trace, and then, because this is in the adjoint, this will be non-zero only if it's abelian. The non-abelian bits are going to go away, because it's 1f. Is that obvious? You know, SUN is generated by Hermitian stuff. No. Whatever. It's true. All right, so I claim that this is a conserved current by the virtue of the Bianchi identity for F. And this is very specific to 3 dimensions because I am using some object with 3 indices. In 4 dimensions, I cannot have that. There'll be some generalized global symmetry with something, some current with 2 indices. And anyway. So what is this thing doing? Well, the things that are charged under this current are some very special gauge field configurations that are called monopoles. So you can have in 3 dimensions, well, in 4D you can also have monopoles, but in 3D they look like local operators in which they're somehow a local, meaning point-like, but they're not built out of the fields. They're determined by specifying some singular behavior of all of these fields in the Lagrangian around this point. So kind of exotic operators. So the only thing that this does is to give charge to monopole operators. We're not going to discuss this anymore. It's just something that I wanted for you to hear at least once. Okay, so we have a very explicit action, and I've emphasized some aspects of it, and I've emphasized that I can think of it as gauge theory coupled to chiral multiplets, but I can also freeze the gauge field and view this as a pure theory of chiral superfields in the background of the metric, which is non-trivial, and background gauge field. So now, we should not lose track of the fact that we are interested in supersymmetric localization, right? By the way, yeah, in Silviu's lecture notes, he gives you in detail the SUSY variations of every single field. I'm not going to write them down. So if you really don't trust me that this is supersymmetric, you can sit down and check it. Okay. Okay, so now the juicy stuff, SUSY localization again. So I just erased what I wanted to do. I want to construct this Q-deformed action, this extra piece in the action. So the action is what I start with, this S, everything that I've written down on the board. And then I'm adding to it a piece. Where P is not the momentum. Something's wrong here. I'm missing a tilde. It's probably this one. Okay, so that's it. That's the action. You can say, oh, how did you come up with this? Unfortunately, it was not me. It was other people who came up with this. This is a little bit the piece of art. So now, this is your action. You can put down the Q and try to really write down equations of motion and ask what are the solutions, and the solutions are very simple. The solutions are, if you wish, the SUSY locus, the fixed points, the critical points, are dj minus I sigma j over A. You can ask, how does D come into the game? Well, I've written down P, but you have to solve the equation of motion of Q times P. And Q acts on itself, but also acts on the fields here. And the transformation of fields leads you to this. So it's really some calculation that you have to do carefully. So all other fields, 0. So it's a pretty simple solution at the end, but the intermediate steps are nasty. Okay? Yeah, right. So what I really mean is the thing I didn't write. The SUSY transformation acts in a certain way on every field. And by this, I literally mean that action. So Q on lambda is to be understood as what sits on the right-hand side of a SUSY transformation of lambda. I started off with the spinner, the one that you were unhappy, but gradually started being happy. That spinner will give me something bosonic here, which you can read in the notes of SUSY, the details of that. That is what I mean here. That hits a fermion, so in total I have some fermionic functional. Then on that whole functional, I have to act with another SUSY transformation with that parameter epsilon. And so this total thing will be some bosonic action. And then I do this for the three terms. So yes, it's a lengthy calculation. Yes. Yes. Sorry. Yes. So you, by this, it's really shorthand notation for this is really what appears on the right-hand side of the SUSY transformation. And then I have to write it out, and this is a bunch of fields. And then this is shorthand for saying, for every field that appears in P, do a SUSY transformation as written in the notes. So these things that I didn't write down explicitly because they're very lengthy. And at the end of the day, things collapse dramatically. And the equations of motion are that every field vanishes except this. Well, when every field vanishes, this action on shell, meaning evaluated at the configuration here, will be very simple, because most of the terms are going to be 0. Okay? Notice also that the saddle points of this action, the critical points, are every field vanishes except fields that don't have kinetic terms. So your path integral becomes an integral over fields that don't fluctuate. So it becomes an ordinary matrix integral. This is a win, okay? This didn't have to happen, because in general, this could be some other, whatever, phi of x being arbitrary, let's say. It could happen. And then, over this field, I have to do a full path integral again. And this will not be a win. But here, it's nice. So, you still have to do some work. This whole big action, the classical action on this locus, evaluates to something very simple. I'm just going to write it out explicitly. Pi I square k trace of sigma square minus 2 pi I r topological a trace of sigma. Okay? So if you have an SUN gauge group, this will not be there even, because sigma will be in the adjoint of SUN, so it will have a vanishing trace. I hope you would believe me, and so I'll have only this term. Okay, so in my formula that I have erased, my job was to evaluate the action, the full action on the solutions of this SUSY, whatever, of this action, and those are the solutions. I've done that. The next step is where you actually have to do work. You have to study every field that has a kinetic term. You have to study the fluctuations of that field around the configurations there. Then those will be Gaussian integrals, so it sounds easy, but there'll be Gaussian integrals on curved spaces, right? So I'm not going to do the calculation, but to appreciate how annoying this can be, even on a sphere, try to do try to do the path integral. This is actually homework assignment. Take the path integral of a scalar field, just one real scalar field, on the curved space square root of g, d mu phi, and then conformally coupled, so whatever, 3/4 over a square, phi square. Okay? Do this. On S3. It will be annoying because you have to first do, this is a Gaussian integral. You're supposed to know what to do. You should expand in, this is the harmonic oscillator, but it's an annoying harmonic oscillator because every field phi of the 3 coordinates on the sphere, whatever, theta, phi, there's phi as a function of phi, priceless. So you expand this phi, which is not a chiral superfield, it's just a real scalar, in spherical harmonics, whatever, y, l, whatever, with some coefficients, ak. So these are now S3 spherical harmonics. These are the harmonic oscillators, and this you have to do an infinite dimensional integral over these modes. You have to do, you have to sum, right? That's why quantum field theory is hard, because you have infinitely many oscillators at every point. All with me on this operation? Do this and appreciate that it's an unpleasant exercise. It's doable, but not trivial, let's say. And then, if you are somehow better than most people and you do this painlessly, do the Dirac operator. Okay? So do a theory, a boring theory of a free fermion, but on a curved space. And then you will actually suffer, I think. If both of these are painless, you just wasted a week of your life listening to me giving lectures. You just don't go to school anymore. Okay. So this is where the meat of the calculation is. You have a number of fields, this complex scalar, these fermions, and for each of them you have to do this kind of analysis. So these are called one-loop determinants because the result is always a determinant of a differential operator, either in the numerator or the denominator, and you have to compute it, and it's in general non-trivial. The result is, I'll just write down the results, and we still have time. So for the vector multiplet, I will write it like this. You get something that schematically reads like that. So this looks annoying because it's a completely general answer. Soon we will find, I will do a very simple example about our friend, the West-Zumino model. And I will, sorry. So this is an exponent. And there's a nasty function, which I will define. Good. So the first thing, so I have to explain what these things mean. I will do so soon. The first thing I will explain is what is the function L of z. Is some logarithms. That's why it's called L. So there's a seemingly nice piece. And then there's a somewhat exotic piece. Plus 1 over pi. And so, some of you may have heard the words polylogarithms. So there's a well-known function, the polylogarithm LIS, which is defined by its Taylor series expansion. It was studied by mathematicians, whatever, 200 years ago, maybe more. So when you put S to 1, this is the Taylor series expansion of the usual log. Okay? But in general, it's, well, I have a function for any S. And here I have what's called the dialog function. So, okay. What I haven't told you is what are these determinants. They have to do with the group theory choices that you have to make. So if you want to keep things completely general, you have to specify a gauge group. It has to be any, it can be any Lie group. So E8, for instance, if you are an exotic person. Or you're too young to know what I mean by the joke, but there's a surfer dude, you should read about it, Garrett Lissy. Oh, I'm being recorded. I will get the lawsuit now. So Garrett Lissy invented a theory of everything that is based on E8. It is wrong, but it is based on E8. So you should go and read about it. He's a surfer dude. He has a hostel, science hostel in Hawaii. Why not? This is the determinant. So if you have any function, these determinants are defined as a product of this group theory data. I will explain what this means. So if you don't know group theory already, you're not going to learn it here, but this WAI are the weights. R is the representation. The sigma is sum over the Cartan generators in the group. Cartan generators. So I goes from 1 to the dimension of the representation. A goes from 1 to the rank of the gauge group. So for the adjoint of SUN, A will go from 1 to n minus 1, and I will go from 1 to n squared minus 1, for instance. Okay, so this is how the determinants are defined. The reason that this is in the adjoint automatically is that it's a vector multiplet. All the fields there are in the adjoint. This is the hyperbolic sign. Here I have a choice in which representation my chiral multiplets are. And that's this R here. Okay. And I should not have called this sigma. I should call this X. Sorry. It's some arbitrary parameter. Okay, so I've told you what the one-loop determinants are. I've told you what the classical action is. And I can just write the full answer now. So the claim is that the path integral on S3 for this model becomes an integral over the Cartan of the gauge group an ordinary integral. So if you fix, let's say, the gauge group to be U1, this will be an ordinary one-dimensional integral. If you fix it to be SU2, it will also be one-dimensional, and so on. So this is a major win for science. A small step for men, a giant leap for mankind. I'll keep on making bad jokes until someone reacts, okay? Okay. Ka trace sigma square A. So for each Cartan generator of the gauge group, I can have independent Chern-Simons levels. So that's why this is so generally written. Our top trace sigma, and then determinant in the adjoint of 2 sinh pi sigma, and then a product over all the chiral multiplets. So this product goes over every chiral multiplet. It's in the representation Rj, and then I have to take this funny exponent of a crazy function. Rj is the R charge of that chiral multiplet. This quantity here is another group theoretic object. It's some integer. So this is the order of the Weyl group. If you don't know what that is, don't worry about it. It's some whatever, 1/2, 1/4, something like that. Okay. So what have we computed? The claim is that SUSY localization ensured that on S3, any Chern-Simons matter theory with n equals to supersymmetry, which is what I was writing down, for any such theory on S3, the path integral reduces to an ordinary integral over the Cartan generators over real numbers. How many of them? As many as the Cartan generators of the gauge group. And then the integrand is somewhat annoyingly nasty, but still an explicit number, an explicit function. So if you wish, if you pick low enough rank of the gauge group, you can put this on a computer and spit out numbers. The only thing that this depends on are group theoretic choices. What is the rank of the gauge group? But also, importantly, on these quantities Rj, so on the R charges of the chiral superfields. So those are free for you to choose. So you would not get a number here. You'll get a function of those R charges. And that's it. So this is the path integral without insertion. So this is, if you wish, the expectation value of 1. The 1 is a BPS operator. It's killed by every action of anything. So it's obviously one of the choices that I can use to compute things by localization. Of course, now you can ask, what about other operators? Can I insert here some BPS operators and run this procedure again? The answer is yes. I'm not going to discuss this. So this is the simplest thing that you can compute. I'm going to stop here to ask for questions, and then I'll make a few more comments in the remaining 15 minutes. Exactly. Yes. Very good point, indeed. The bodies are buried here. So the thing that you're describing is done. So these one-loop determinants. So if you do the homework that I told you to do, this homework, on S3, I don't have IR divergences because it has it's regulated by the size of S3. So the IR divergences that I could have if I have a massless scalar will result in powers of little a. So those are cured because I'm on S3. That's the purpose of life of S3. The UV divergences will not be cured. So this sum here over the harmonics will go all the way up to infinity. The eigenvalue will increase of the Laplacian, right? And so I'll have infinity. But those infinities are precisely the things that we cancel with counter terms. So that's what you have to do. you have to cancel infinities by adding counter terms. This is a renormalizable quantum field theory. So in this case, I have to add only 2 counter terms related to the curvature of the sphere, so the Ricci scalar and the cosmological constant. So you have this action plus the action of the counter terms with only 2 coefficients to fix for infinitely many observables, you know, how the usual story, and you cancel all the divergences in this way, and this is the finite answer. So this is the renormalized one-loop determinants. Yeah. Does this answer your question? If you want to really be annoying, you can then, but I've learned that the counter terms I use in quantum field theory have to be compatible with the symmetries I want. So then you should really worry that the counter terms that you use are actually compatible with the supersymmetry of the problem. And most people ignore this. You can be one of those people. Or you can be a careful person and prove that they are actually okay. Yes? Yeah, so this is the zeta function of de facto here, yes. Yeah, yeah. It's, yeah. Any other questions? No? All right, so we now can forget about the gauge field again and study our friend, the chiral superfield. So, for instance, you can ask, well, what is the simplest three-dimensional n equals to 2 quantum field theory I can think of? Well, the simplest one is a free chiral superfield. Okay, so let's start computing. I was here. Examples. First one is a free chiral superfield. Then the dimension of the operator phi is 1/2, and it's equal to its R charge by convention. That's a protected operator. They have to have, so that's the simplest model. So then your job is to compute. People usually talk about the free energy. Again, funny notion, because I really don't have any notion of temperature here and thermodynamics, but minus a log of the partition function in thermodynamics is called free energy, so I will use the same name. So this is minus log of what I just computed, and this big mess there, most of it is just gone. I don't have a gauge group, I don't have a Weil group, I don't have this Singe determinant and so on. This is just a free, the representation is trivial, and this is just a free chiral. So what you find is that f is minus this function L evaluated at argument 1/2. Because you see, sorry, this is, sorry, this is badly written, 1 minus. So this is L, a function L, then 1 minus the R charge plus the value of this parameter sigma. But I don't have sigma in the game, so it's 1 minus 1/2, and it's very easy. So then the function L is written up there, and you can prove that when you put the argument to be 1/2, you get a beautiful answer. 1/2 log 2. So this is approximately, so you can put this in on a computer and ask what is the approximate value. It's some number like that. Okay. So this is really it is a number because I've made all my choices. I fixed the gauge group to be nothing. I fixed the R charge to be 1/2, and so this partition function becomes a number, and it's this number. The second example is the critical Wess-Zumino model. Then the superpotential is non-trivial. phi cubed, from which we learn that the R charge is 2/3 R. Right? This is what we've been using for a couple of days now. So then, by the same token, you find the f of S3 for this critical Wess-Zumino model is minus L of 2/3. As far as I know, that this is not anything nice. It's some transcendental number, which you can nevertheless put on a computer and evaluate to some accuracy. Okay, so I got another number. So at this point, you can ask yourself the existential question, I signed up to do physics, what am I doing? Because these are some random transcendental numbers. Well, the point is that this simple analysis illustrates a broader physical principle that people have understood as of lately. F of S3, this observable, is something that knows about RG flows. So the RG flow intuitively is something that as you lower the energy, you have to integrate high energy modes and only care about the low energy modes. So you lose degrees of freedom, the high frequency stuff, and you have only the low frequency stuff. That's the intuition of Kadanoff and Wilson and Polakov. So then, if you have this intuition, you should be asking, well, is there some physical quantity that measures what I have integrated? You know, everyone can do this thing with the spin averaging and so on Wikipedia, but what can I compute? Can I compute something that is finite and somehow decreases along RG flow, some kind of a measure of the number of degrees of freedom in the problem? The reason this is hard is that quantum field theory has infinitely many degrees of freedom. At every point, I have infinitely many harmonic oscillators. So yes, I have infinity. When I do an RG flow, I still have infinity. So how do you compare infinities? Right. So this function achieves that. So the claim is that the free energy of a quantum field theory on S3 is monotonically decreasing along an RG flow. I'm not making a claim that this is the only function that does that. I'm making the claim that this is one function that does that. This is very deep, okay? This is, we're learning about this complicated operation, RG flow, that relates high energy physics to low energy physics. And so this is a deep quantum field theory fact, which is illustrated by these two random numbers. They're not random, is the point. So this number, you may know, you may observe, is bigger than this number. Okay? And why is that? Well, the free chiral superfield without interactions, that's the asymptotically free limit of the Wess-Zumino model. So we have an RG flow, which in the UV is a free chiral superfield and has this free energy. And in the IR, I have this interacting critical Wess-Zumino CFT with this interaction. And so I have reduced somehow the number of excitations I can have, and this is reflected by the fact that this number is smaller. So the claim is that in every QFT in 3 dimensions, actually, with or without supersymmetry, this is a monotonically decreasing function. That claim was first observed exactly in this SUSY context. So this is one thing that, some kind of a payoff of all this abstract nonsense is that we learn a physical principle that seems to be valid in non-supersymmetric quantum field theories. Of course, computing this for a non-SUSY QFT is hard, but there is some evidence in the 4 minus epsilon expansion at large n and so on, all these approximate methods that this is actually true. So this thing is called the F theorem. Okay, I'm almost out of time. I think this is the last thing I wanted to say today, but let me just check. So yeah, the F theorem is that F on S3 in the UV is greater than F of S3 in the IR. That's really the theorem. It's a continuous monotonic function, decreasing, monotonically decreasing. Okay. For a moment, I stop, and if you have any questions, ask me. Yes? Correct. So in the free case, indeed, it's somewhat confusing because I have actually infinitely many symmetries. I have this whole tower of higher spin currents. Everything is fixed. But I want to think of the chiral superfield as, well, as one of these protected multiplets, so I know the dimension, and so I assign an R charge that is equal to the dimension. So it's a little bit artificial, if you wish. You have to wait until tomorrow morning. This will be the lecture tomorrow morning. Yes. So there's a deep question, how do I fix these R charges? Because they seem to be parameters that, yeah, I can play with. And there's a unique way to fix them if you insist that you have conformal symmetry. If you don't have a conformal symmetry, they're free parameters. That's the short answer, but there's a long answer, so you should wake up early and come, and I'll tell you the answer. Yes. By the way, this number you can compute without supersymmetry, because this model is really one complex scalar and one complex fermion. So if you do your homework assignment, you get 4 things to compute, and when you add them up, it will be 1/2 log 2. So I didn't have to assign this R charge. I should not be even thinking about supersymmetry, if you wish. And I will still get this number. But it comes out of this more fancy analysis in this way, by assigning R charge 1/2. Yes. Yes? No, it's independent because, good. In general, in quantum field theory, you learn about counter terms that cancel divergences, and fine, that's a good thing to learn about. But what is not frequently emphasized is that you can also have finite counter terms, meaning choices to add to your action which contributes a finite piece. And so that can be added with any coefficient, and this will mean that a certain observable is completely dependent on the choice of that counter term, and this is called scheme dependence. So if you want to be a careful scientist, which you should want, you have to prove that this observable f of S3 in 3-dimensional quantum field theory for any renormalizable quantum field theory does not admit finite counter terms. In which case, yes, there's the divergent pieces, but those we always have to cancel, and it doesn't matter how you cancel them, and there's a unique finite piece that cannot be affected by a choice of scheme, and that's, yeah, one can prove this, yes. Not obvious at the moment, but yes, it can be done. And it's an important thing to do because if you want to claim that it's a physical observable, it has to be scheme independent. Other questions? No? All right. So someone online or?
Yeah. So I don't know if I get it correctly. You can analyze these decreasing of this quantity f along this RG flow just because you know that this free theory goes to the critical Wess-Zumino theory, right?
Well,
So,
in this example, I have independent kind of information about this RG flow, but in general, in QFT, RG flows are hard. And so this principle kind of orients me when I study the RG flow. I may be confused, I may find some random CFT somewhere, and one way to understand where does it sit in this RG web of possible RG flows is to compute this F somehow, and then see how big it is, and then I will know that it's in the UV of this one and in the IR of that other one. So it's kind of a label that you should attach to every CFT.
okay, I see. And another...
Yeah, just to emphasize, it's not easy to compute in general, right? So this F theorem, well, people claim to have a proof by some abstract tools. I'm not going to talk about it, but yeah, it's not easy to compute.
Okay.
Yeah.
And another question is that earlier when you added the Q exact term, localization term in the action, it was parameterized by some T, and you said that it was arbitrary.
Yeah.
It was just an auxiliary parameter.
Yes.
So but when you look at twisted D equals 4 n equals 2 in Witten's paper, the whole action is Q exact, and he makes a comment about the theory being independent of the coupling constant. So how should I see that statement in this?
Yeah. So good.
It is independent for the sector of BPS.
Right. So maybe, well, I will give you a short answer. I mean, first of all, you're asking me to comment on Witten's paper, which is an interesting thing. Everything he says is true, okay? So that's the first comment. But yeah, this is a fairly exotic situation. So the content of that paper is to use 4-dimensional n equals to 2 Yang-Mills theories to learn about 4 manifolds. So essentially what he does is he does this topological twist, which means that when you have an R symmetry, this symmetry that doesn't commute with the spinors, you can turn on a background magnetic field of that R symmetry, and you can turn on a background metric for your quantum field theory. For those of you who want to eat or whatever, watch Tiger King on Netflix or something, you know, just you can go. But those of you who want to see me ramble, you can stay. You have this structure, and then very, very schematically. So I have some, so the setup is that I have a 4-manifold, M, and I have a 4-dimensional n equals to 2 quantum field theory, and this unnecessarily has an SU2R symmetry. Okay? So now, this A is a background magnetic field for this SU2. Okay? This is the spin connection for the metric on this manifold. Okay? Good. So Witten's idea is to ask, on which curved manifolds will I have a spinor? Well, the answer is known to mathematicians, and on most of them, I don't have a parameter epsilon that I can use to generate supersymmetry. So on most curved manifolds, the supersymmetry of this quantum field theory will be broken. However, if you tune the background field to be equal to, I should not be using A and B, I should alpha, beta or something. If you do this, you cancel these two terms against each other, And then you just need a constant spinner. Constant spinners exist on all spin manifolds. Spin manifolds are, there's infinitely many of them. They're characterized, there's some characteristic class, the Stiefel-Whitney class, which if you compute and if it vanishes, you have a spin manifold. So many manifolds are spin. So you just found a way to put a SUSY QFT on many, many more manifolds that you can naively kind of expect by doing this twisting. Okay? So in some sense, you are redefining the tangent, you are mixing this gauge bundle and the tangent bundle of the manifold. You are kind of annihilating them against each other, and you're making a locally flat manifold. So the structure group, the thing that acts on the tangent bundle of a 4 manifold is SO4. SO4 is famously SU2 times SU2. And then you can use this SU2 to cancel one of the products. So you kill this. So now you go from what's called an SO4 structure manifold, which is any manifold, to an SU2 structure manifold, which are special manifolds. And you can prove rigorously mathematically that SU2 structure manifolds admit always spinners. So this operation can work only if this is big enough. Okay. So that's, I took a lot of time to just explain the setup. So then you just constructed a QFT on any 4 manifold, spin, but okay, any. And then you can ask, what is this QFT? What does it compute? Well, it turns out that it computes numbers. So the correlation functions are independent of the position. So they are independent of the metric of the manifold, because in this way you also modify the action of the theory. And the result is a topological quantum field theory. And arriving at this result, the arguments involve a lot of this kind of Q exact and Q closed stuff. But strictly speaking, this is not the SUSY localization that we have here, because this is a simpler variant of it, where the QFT really, all endpoint functions are just numbers, and these numbers are very deep and important. They're called the Donaldson-Witten invariants of the 4 manifolds. These are topological invariants of the 4 manifold. Okay, so this path integral is somehow a tool, a gadget that allows you to study the mathematics of 4 manifolds in a deep way. Our stuff, we're really studying the physical theory, meaning that we don't have a topological theory. Our endpoint functions will depend on the position and on the metric and so on. So that's, I don't know, comparing the two setups. But indeed, for him to show that the path integral reduces to this, he uses an argument which is a version of this SUSY localization. Was that clear for the person online who asked?
Yes, thank you.
Yes. All right. Good. Thanks.